going to have Tomaz do the last presentation of the series.
Okay, so I'll start again showing a couple of slides just to recap what we have done the last time on Wednesday. I was told that I should not use slides and board at the same time, so I was tempted to write stuff on the board, but I'm just now showing a couple of real physics calculations from the matrix product representation of the NES for the XXZ circuit and XXZ chains. Actually, that calculation is for the chain, so it's a analogous result for continuous time. What I want to show here is that there is very interesting physics transition in the steady state of boundary-driven XXZ chain, which shows transition between ballistic and insulating transport when you go from delta larger than 1 to delta less than 1, or vice versa, delta less than 1 to delta larger than 1. And critical case, or the intermediate case, where delta is equal to 1, the SU2 symmetric case, exhibits some interesting anomalous or subdiffusive transport where current, this is evaluating the current as a function of system size. Now, little n in this slide is a system size, and it shows like 1 over n square of the current scaling. So, so the MPS that I showed last time, of course, if you want, okay, so just for the people here, if you want to compute steady state observables, right? You do something which is analogous to what people do in ASEP, right? But now you have two replica. You have like 2 row, if you want, transfer matrix representation of the density matrix. So it's slightly more involved if you compute observables, because you have to, take the tensor product of two replicas, and this makes stuff a little bit more interesting, if you want. Anyway, there are only experts here. You know exactly how you should then proceed, right? But the point is that results are kind of quite non-trivial, and they find this is the scaling of the current, and this is the scaling of the spin profile. So the spin profile also shows some kind of interesting features. In the critical case, it is a cosine shaped profile. Delta larger than 1, it is kind of a kink shape profile with with a very narrow transition, which scales as log of the system size. And in the delta less than 1 regime, it's just a ballistic profile, flat spin. You can also use the same kind of metrics ansatz to compute 2-point functions. I'm just giving you some results. Of course, for details, you can check the papers, but it's just to illustrate. You can do 2-point functions. This calculation is already more involved, right? What you get is a result which is kind of interesting. For people who know similar results for SEP, right? If you forget about the trigonometric factors, this is exactly the 2-point function people find for SEP. Now it has an additional trigonometric factors which are related to these cosine shaped profiles. So that's a 2-point function. It has this kind of long range correlations. What is kind of even more interesting physically is the fact that you can compute Drude weight, so ballistic contribution to the transport coefficient, so ballistic transport coefficient, the Drude weight at infinite temperature in particular for the XXZ chain for delta less than 1. And at roots of unities of this, at root of unity points, when Q is a root of unity, that is when delta is a cosine of a rational multiple of pi, you find these little spikes. You find this kind of fractal dependence of Drude weight on anisotropy of the model. Which is physics-wise very interesting, but mathematically it's a consequence of the fact that at root of unity you have a finite dimensional representations of the Lax operator. So the auxiliary space, even though formally at complex spin carries an infinite dimensional representation, at root of unity this representation collapses to a finite dimensional one, and that makes stuff quite interesting. Okay, that's this slide I already showed. If you do the same thing for the circuit, you get a result which is exactly analogous. That was done a couple of years later, but it's exactly analogous. So I think that's all I wanted to show. Then I go back to my chalkboard. So I'm not sure I'm able to do that myself. So please can you just switch back to the board?
Slides.
Yeah, no more slides for today. So if you remember last time, I wrote a steady state density operator for the non-equilibrium steady state in this factorized form. Was some prefactor, and then there was omega dagger, and this omega had this nice factorization in terms of the Lax operators. This was an auxiliary space, right? So this is that has. And now, I mean, this of course, I mean, I won't go into much details here, but I just want to stress this most interesting kind of byproduct of this result, right? I mean, this is a steady state now of our quantum channel, right? And byproduct of this result is that this rho infinity also forms. I mean, since it's a it's a fixed point of a quantum channel which has only dissipation at the boundaries, then it means that it's also kind of related to a conserved quantity, right? I mean, essentially, you can form. I mean, it's not maybe clear from this representation, but you can form an operator which is the following: z of lambda, which is derivative with respect to a complex spin, r omega, and evaluate it at s equal to 0. And if you look at how this operator behaves under the mapping, so with the unitary circuit, like make a one-time step Heisenberg evolution of this operator. So this is like a time derivative, if you want, a discrete time derivative of the one-time step dynamics of this operator, then you find that this has only boundary terms. Now, I will not go into detail of deriving this. It's kind of easy to show, but as I say, I mean, I probably want to finish this quick and go to the third lecture, but I still want to stress it's kind of extremely interesting that in this case you get an operator which is in thermodynamic limit conserved. Now in finite system, of course, it has boundary terms. These boundary terms, okay, you can ask, okay, they are local, but you know they're effectively local. They're not exactly local, right? So you have to be kind of I mean, you have to kind of know how to characterize locality of these terms. So in some sort of appropriate sense, they are local, right? So you can say they are glued at the boundary. And this operator is kind of extensive, right? So it's quasi-conserved, or it's conserved in thermodynamic limit, and it's extensive, right? So you can look at this operator is not Hermitian. I mean, the way it's written is not Hermitian, but it's extensive in the sense that its expectation value at infinite temperature is growing like volume. Okay, and yeah, and this is something that actually then generates kind of quasi-local charges. For example, if you look at how it behaves under the spin flip, so for example, you define a spin flip. So you flip all the spins in Pauli basis, then that guy is not symmetric on the spin flip. Unlike, for example, the standard transfer matrix that I wrote in the first lecture, the standard transfer matrix, which is obtained through the fundamental representation of the auxiliary space, of the unitary representation of the auxiliary space, satisfies this symmetry relation, right? You can flip the spin and you get the same transfer matrix back. This is a kind of canonical transformation, right? So this is is invariant under this spin flip canonical transformation, but the Z is not invariant, right? So, and that's actually very interesting because the spin itself is also not invariant under spin flip, but it changes sign, right? The SZ will change with anti-commute with sigma x, right? So it will change sign. So if you form a Hermitian operator, Q of lambda, by taking the anti-Hermitian combination of the Z. Now these operators, of course, are analytic functions. They depend on some, there's kind of analytic functions of a spectral parameter lambda. So they are the whole family. So this is, okay, so you just take this combination, Hermitian combination of these guys, and then you anti-commute, like fraction anti-commute. I mean, they are kind of matched to its minus. So it really looks like a spin or a spin current, right? And it is the same as for the spin current. For example, take a spin current. Now, spin current is something like that. Not worrying about possible multiplication by powers of 2. Maybe it's a factor of 4, doesn't really matter. I mean, this is the kind of how spin current in spin chain looks like, right? And what is crucial now is that this conserved quantity has non-zero overlap with the spin current. This is, of course, I mean, a kind of expectation in at high temperature or at infinite temperature state. I mean, here I'm talking about infinite temperature state expectations. So spin current has a non-zero overlap with this new conserved quantity, right? I mean, unlike for all the, again, the old transfer matrix that generates all the local conserved quantities, a vanishing overlap with the spin current, right? Because of the diff of the opposite spin flip symmetries, right? So there is a Z2 symmetry, and the chain has a sector with positive and negative observables, which are symmetric and anti-symmetric with respect to spin flip, and all the kind of local charges which derive from the transfer matrix are even with respect to spin flip, but this solution of the boundary-driven spin chain, stochastically driven spin chain, can be odd. I mean, can break this spin flip symmetry, so we can derive an odd conserved quantity, and this is relevant for spin transport. I mean, this is how you show this kind of fractal Drude weight, right? Okay, so right. Now I wanted to discuss another kind of setup, which is very recent. I mean, this has been kind of an old story, right? I mean, from early 2000s, I mean, early 2010s, like 2011, 2013. And probably I didn't have time on Wednesday to mention what other models we can solve with this same approach. We can do higher spin models, SUN models, SUN integrable models. We can do Hubbard models, Fermi Hubbard model. They all, I mean, you know, they will behave quite similarly. I mean, the structure of the solution of the steady state is quite similar. What is kind of not clear, and this is something that I want to return in today's lecture, is how this fits to the general framework of integrability. Because what we are after now is just some kind of exact solution for the steady state density matrix. And it's not clear whether this really means integrability of the time evolution, right, of the quantum Markov chain. I mean, we have now a quantum Markov chain, right? Markov chain N or M, right, which is 4 to the L by 4 to the L matrix, right? The question is this an integrable model, right? Can this be diagonalized by beta ansatz? And it's not clear. I mean, we know a few examples, which I will discuss in the second part of today, but We have only very few examples, and we have no idea how to generally approach this problem. In particular, the stochastic boundaries that I've discussed so far, they seem not to be giving integrability. So it seems that this kind of superoperator M that I constructed so far is not integrable. I mean, there are kind of empirical methods to check integrability, like you check level spacing. For example, this complex this quantum Markov chain generator is a non-Hermitian matrix, so it has a complex spectrum. You can check statistics of these complex eigenvalues, and you see that it conforms to Geneva ensemble of random matrices, not to Poisson ensemble. So these eigenvalues are correlated, which means that this cannot be integrable, because if you have an integrable system, you expect that there is so much symmetry that the eigenvalues cannot be correlated. So they should be kind of Poisson distributed. Yeah. So I mean, that is a kind of well-defined numerical procedure how to check that, and it's clear that.
You remind us how M is related to rho.
So sorry.
Remind us how M is related to rho.
Yeah, I mean, rho is just a fixed point of M, right? So now rho infinity is just a fixed point of M, but now what we are after maybe is an eigenvalue equation, right? And the question is, I mean, how does the spectrum of M compute, right? I mean, are we able to compute the spectrum and excitations rho lambda, right? This will give us then the finite time decay, finite time relaxation. For example, I mean, the most interesting object would be the spectral gap. So what is the lambda which is closest to 1, right? I mean, you've seen pictures like that in the Sylvan stock, right? For the classical stochastic models, I mean, you typically have spectra which are somewhere in the negative part of the complex plane, right? Well, I mean, for the M, these spectra are within unit disk. So the eigenvalue 1 would be the steady state, and then the question is which is the closest eigenvalue and what is the gap? How does it scale, right? This is all interesting questions, but they can be answered in only very specific models. I will discuss one model today where this question can be answered, but we basically know 1 plus epsilon models for which this can be done. So it's really an interesting open question how to approach integrability of this type of quantum Markov chains. But before going there, I will just sketch, but since I see I have not enough time to complete my program fully, so I'll probably be just quickly sketching what else can we do. That's a very recent paper. I will just sketch a result from a very recent paper together with Slava Popkov. That's 2-3 months ago. 06731, where we were able to solve the so-called reset-driven XZ chain, XZ circuit. So similar as before, our circuit, but the class of stochastic boundaries now seems to be much broader. It does not include fully the boundaries I've discussed so far. So these stochastic boundaries are in some sense more general, but in other sense are much more restricted. So I will be more precise what I mean by reset-driven quantum circuit. So let's say I will again make a kind of cartoon of what we are, yeah, something like that. Let's take, and then doing something like that. These are so let me name these qubits like 0, 1, this will be L, and this will be L plus 1. So I'll use this enumeration since I will try to then trace out the qubit number 0 and L plus 1, because they are really not relevant because they are kind of reset right after each application of the half map, right? Each application of each layer, I do a trace, right? This is now in operator notation, so this is what I will now denote as W, and W is the doubled gate. And this is what acts on density matrix. So this is U and U star behind it. And U again is 1A, B, B, A1. It's a 6-vertex model, right? It's a unitary 6-vertex model. This A now can be, okay, I will not go into detail. So A can be arbitrary, arbitrary Q-deformed 6-vertex model in unitary representation. This is the trace. So this circle means a trace, so we're taking a trace, right? And this guy means after taking the trace, you take a tensor product in some state, which I will denote as row left, and here as row right. So this is why it's called reset, because it implements a kind of a strong measurement. I mean, it basically just forgets about the state of the qubit and it puts it in a fresh state. I think this state will be a pure state. And here another pure state. Okay, so now this is what we call a reset-driven XXZ circuit. So it's kind of quite generic, right? I mean, it's also very well suitable for what people in quantum simulators do these days. I mean, for example, I know at least that a group of Google has a tool in their toolbox, which they can use to program their machine, right? They have this reset channel as part of the standard kind of programming toolbox. So you can, I mean, they also had a paper in Science last year where they have already measured observables in this type of circuit, right, with reset driving, so stochastic driving in terms of reset gates. So, but right, so now I don't want to go maybe too deep into that, but let me just reiterate that again. Now we can write a steady state for this circuit. So again, now this we'll just finish the definition. Now this M again is factorized in 2 layers, which are called an even, and even layer is W tensor L minus 1 over 2 times tensor KR, and odd is K left tensor W L minus 1 over 2. And sorry, because now I want to also to do what I will denote as M tilde, which means I will trace out the zeros and the L plus 1 qubit. So I will define M tilde as tracing 0 and L plus 1 qubit M. It turns out if you do that, you can do that on arbitrary function of K tilde, so you can take an arbitrary power, an arbitrary iteration of the circuit. This will be still true because I mean, you easily see what is then. I mean, when you do the trace, right? I mean, basically you just forget about, you do the trace, and then what you get is basically M tilde, which doesn't have the 0th qubit anymore, but it has a machine which is applied to first qubit, which has this structure, right? So what I have now is basically definition of this reduced gate, right? Which will be taking a trace, putting it into row L, and this will be what I denote as a left. Okay. And similarly, I do for the right. Row right, taking the trace. This is what I denote as K right. And then this reduced gate then can be factored in this way. So we can immediately remove 2 qubits. And then I have this particular form of these boundary gates, right? And this is kind of quite, it's lots of free parameters, right? In this case, these gates have, you can write explicit Kraus operators, which generates these two gates, these two quantum channels. I mean, they're quantum channels, right? They're completely positive maps over a single qubit. And now we have this kind of definition, right? We have x-axis circuit and this reset Kraus maps. Yeah? And right. And now how do we solve this problem? Well, we write some sort of solution of Young-Baxter relation, which has this curious inhomogeneous form. I'm calling it inhomogeneous solution of Young-Baxter equation. So we take again an auxiliary space which is infinite, which is spanned by a vectors, a basis, which I will denote as J. So now this, we take two types of Lax operators. There will be L plus and L minus. So there is a diagonal part, and then there is dn. Probably doesn't make sense to write all the details. It's so, I mean, just to, what are these matrices? These matrices are 2 by 2 matrices, which depend on an external, this one explicitly depend on an integer. So it encodes a Q parameter and encodes some free complex parameter Z. And then this guy involves a spectral parameter to diagonal matrices. And there is a similar expression for the L minus, which I will not write out. And the point is that this satisfies sort of Young-Baxter equation, which now, I mean, this is, it's just to show what is really crucial. I mean, here, right, is to have so now, yeah, this is now I have to flip, of course, minus plus, and then there is U and plus 1. Okay. And then, so there is another set of, I mean, then you have to complex conjugate these equations, right, to go from bra to ket. So then you get what we denote as double L operators, right? Double L operators will have 2 auxiliary spaces. Here there will be complex conjugation. And right, and then you want that there is a pair of density matrices which are intertwined with the 2 pieces of the quantum channel. So after the complete cycle, they are conserved. So if you apply this MO on this equation, then you get rho infinity is M rho infinity. So in this case, I mean, but it's better to write it like that because it's a kind of, I mean, 2-stage process, right? So we need that anymore. Then we have some left state. There's a right state. And here the difference is that we start with L minus. And Now the left and the right state are the states from tensor product of two auxiliary spaces, which are called A and B. And now what is kind of remarkable with this solution is that we need actually, unlike in the previous solution where we had a factorization, remember there was omega dagger, which means a boundary state was factored, right? It was at around 0 cross 0 tensor 0, right? But now boundary state actually is a non-trivial correlated state between the two replica spaces. So you can interpret these guys as kind of density matrices, right? I mean, now this is like the bra and the cat of density matrix. So these guys are like coefficients of two kind of boundary density matrices. So these are like kind of density matrices. They are determined from the boundary equations. So they are determined from the boundary equations of, now you can imagine what happens, right? Now you plug these guys into these equations and you implement these Young-Baxter relations. These Young-Baxter relations allows you to flip plus to minus and minus to plus, right? Except at the boundary. At the boundary, you have to solve boundary equations. Then on the right, similar boundary equation. And these boundary equations result in, well, identification of boundary states. So that gives us recurrence relations between these coefficients. And it turns out these recurrence relations can be uniquely solved. So there is a unique steady state. I mean, you can show independently using some well-known theorems that this quantum Markov chain satisfies sort of quantum Perron-Frobenius theorems. It has unique steady state. And that steady state, then since it's unique, right? I mean, once you compute solutions, you know that this is a unique solution, right? So it's actually, what is remarkable is that what you get then is, I mean, explicit recurrence for these two boundary states, which you can solve explicitly. And it turns out that these R and L have a rank, which is larger than 1, there's a rank 2. And this is the first time I see something that has a rank which is bigger than 1. So, well, at least there was one conjecture which, based on experience, we kind of assumed earlier, is that always when you try to solve this type of problems, you will get this factorization of two auxiliary spaces. And so there will be no coupling between two auxiliary spaces. Now, this is the first example where there is non-trivial coupling between these two auxiliary spaces. So it's kind of interesting. But you see, I mean, we are just playing in the dark. And sometimes we discover something new and then, okay, we are excited, but, you know, we are still kind of, I don't think we see the big picture yet. Okay.
Where does this L matrix come from? Does it have an origin? Is it some kind of higher spin continuation?
That's a good question. Yeah, I've been discussing with Jan for the past days. I mean, where does this come from? I mean, is it part of your more general solution, right? I mean, you can maybe.
I know. Yeah, I know. We should talk in detail, but I know exactly where it's comes from.
Okay, good, great. So yeah, I mean, I think it's. You see, the experts already know. So I mean, we kind of.
Who's on the I spin. Okay. S to 0, we got it. Okay, that's what. Yeah. Or S to infinity. Yeah. Okay. Good. So now this is all that. I mean, now let me go to my last 25-30 minutes, which will be nominally the third lecture. But since I don't have so much to say, I think it'll be okay. The third lecture should be the most interesting, but the least. No, I mean, what we have is, I mean, the amount of material is the smallest, which I want to cover. So there are not so many things I can say. The question now, I mean, what are really the integrable models, right? Integrable open Kraus circuits. Integrable open Kraus circuits. So the question is, now let's simplify the problem a little bit. You can of course ask the question, what boundaries will make everything integrable? That's one question. For that, I already admitted that we don't know much and that we don't know how to proceed. You may ask whether these channels can be written as a double row transfer matrix a la Ljubljana with some reflection matrices at the boundaries. My answer is probably not. At least insofar what we have tried gave only negative answers to that kind of questions. We even have a paper with my postdoc Chiara Paletta showing that under other kind of generic assumptions, there is no solution of this type. So there is.
Sorry, so your speculation is that this elements are not kind of fused K or not K matrices?
Yes. You disagree?
Yeah, I can show you that. So I think your rows are double row transfer matrices with the bosonic.
Well, okay. So yeah.
And then what you want is another double row transfer matrix, which is your circuit,
right,
to interact nicely with this.
Yeah.
So the two.
That's what we want. Yes.
Yeah.
But that we don't know whether we have.
No, but there are.
You know how to
put it in the right framework. There are ways.
Okay. But that's actually, that would be really great to find because we have independent, indirect evidence that these circuits should be integrable. As I told you, the previous kind of longitudinal driving with this sigma minus, sigma plus, for that we had numerical evidence that it's not integrable. But for these reset-driven circuits, we have independent numerical evidence which suggests that spectrum is Poisson, so it should be integrable. So it's consistent with what you are saying. But I'm just not able how to find a double row transfer matrix representation of the channels.
And one more tiny question is: these elements they satisfy recursions in J and J prime? Is that correct?
Yes.
They're fully factorized.
They're fully factorized. Well, not fully because they have rank 2. So you need. I don't know. I'm sure what would you mean by fully factorized. They can be written as two terms of this form: AJ B del prime plus AJ prime.
Right here.
You need two terms, like two factorized terms. Yeah, that's why I'm saying they have rank 2. Yeah, and then each of these vectors can be worked out explicitly. There are some 400 symbols or something.
Yeah. Okay, so discuss that. We believe this comes from a fused K.
Yeah.
Okay, let's talk about it. Yeah, that's great. Yeah. Let me finish the lecture then. That's great that when you learn during your lecture. Okay, so now let me just flash something that's much simpler because it's not boundary integrability, but just bulk integrability. So the question is, can we foresee a model which is homogeneous in space, which would be integrable in the standard sense, so that the gate would satisfy Yang-Baxter equation, and on the same side, on the other hand, it would generate a non-trivial dissipative quantum system. Yeah. So now the question is, homogeneous translation invariant. So I would like to make again M, which would be a two-layered circuit, right? This guy I will do like that as before. This is like first lecture. Now, the only difference is now that I want this upright M, which acts on 2 qubits, right, to have a Kraus form, non-trivial Kraus form. So say this is L is from 1 to mu. Mu is some rank, some Kraus rank. And diagrammatically, you can think of this as two-layered
circuit, right? I mean, again, something that acts against the matrix, but now it has several Krauses, which means there is another kind of wire here, which has L indices, right? Which has index L, which runs over n mu values, and that means summation over Kraus operators, right? This would be the diagrammatic picture, right? And now the question is, is there such a integrable circuit? And I would just like to conclude with our construction and then to give you some update on the references that have appeared after that, which generalize this construction. But the one kind of the most pedagogical construction is the Shastri's R matrix for the Hubbard model. So there is, so the question is, can you interpret? Now what we need is, for example, we want to have qubits, right? The simplest model would be model of qubits, where this would be a two-state wire, right? So the two-wire state would be four-state wire, right? So we want to have like a system of four states, right? Tensored. So these are like electrons with two spins, right? So the natural candidate is the Fermi-Hubbard model. Fermi-Hubbard model you can also understand as a spin ladder model. So when you have two species of spins, let's say sigma and tau spins, and each wire then has again four states. So it turns out, yes, that this is exactly the Shastri's R matrix that you can interpret as a quantum as a Kraus map, as a quantum channel. Okay, so let me just give you kind of a 15 minutes derivation of that. I mean, not really derivation because I will not complete any proofs. I will just state observations. So the answer is yes. An example, M is an R matrix. Is the so-called Shastri's, the Shastri's R matrix. R matrix of the Hubbard model. Of the Hubbard model. So how do we construct that? But now I will just give you a construction which is more kind of close in spirit to constructing quantum circuits. I mean, Kraus maps. So what will be the analog of of the two species of electrons, spin down and spin up electrons, or two species of spins, sigma and tau spins? Well, the analog will be the forward and backward copy of this Kraus map, right? So since again we have a kind of in this vectorized notation, we have two copies, two replicas. So one will represent spin up electrons or sigma spins, and one spin down electrons or tau spins. So now let's just take a single replica first and start with the free fermion R matrix or R check matrix. So start with the R check matrix, which for free fermion, this is just a 6 vertex, but for free fermions you can have a particular relation. So I will write it now in terms of ABC, IB, C. Of course, there are different gauges in which you can write this. I will choose this gauge. A is cosine lambda, B is sine lambda, and C is equal to 1. We can note that R check is real orthogonal. Real orthogonal for lambda, which is imaginary. It will turn out that the interesting realization of our parameters in this game will be purely imaginary later, but for the moment this doesn't really matter. So now let's take two replicas and write little R check matrices on two replica copies. So R up will be our guy, and now rho I will again denote as two indices. Let's call them JL, and column I, so IJKL. Now this will be unit matrices, Y matrices, IJ. So nothing on the second copy, then on the second particle, Okay, L, and nothing on the second copy. This will be, yeah, and summing of repeated indices. Now, for the second guy, it's all the same, just flipping the copies, of course. All right. And of course, this guy satisfies the Young-Baxter equation, right? But of course, this is trivial. But now what we can do, we can now couple two terms formed from these guys. So let me now denote little r check. Little r check. Which is just a product. This is just, yeah, a product of two free, tensor product of two free fermion R matrices. And then I will denote curly R. Now I will make an ansatz, curly R, which depends on two spectral parameters in a non-difference way. So I should write them separately. And there will be some multiplicative parameters beta. We'll have lambda minus mu plus alpha. There will be lambda plus mu. And then here there will be some weight, which is in diagonal. This is a so-called decoration of Shastri. Yeah. And then this guy satisfies Young-Baxter equation. Great. Or Young-Baxter equation. So. R nu. And yeah, so this satisfies Young-Baxter equation if the following is true, if these weights satisfy the following constraint. So alpha over beta should be related then to spectral parameters, cosine lambda plus mu divided by sine lambda minus mu, tangents, hyperbolic tangent, h minus L. And what is h and L? Where h and L are determined from these two constraints, that sinh 2h divided by sine 2 lambda is the same as sinh 2L divided by sine 2 mu is equal to parameter u. So now you can say that this h and L are determined from three free parameters, lambda, mu, and u. So this is the so-called spectral parameter, and this is the so-called interaction parameter. So this is coming from now Hubbard physics, right? I mean, when you start from some Hamiltonian, I mean, the physics-wise, you would start from Hamiltonian, where U represents interaction among electrons. But now for us, this is just some formal solution for some solution of Young-Baxter equation, which turns out that it can be interpreted as a quantum channel. Okay, so now probably now it's yeah, just okay. So maybe that's one more thing to write, and then yeah. So there's one more choice, which is kind of arbitrary because normalization of, I mean, you can multiply R matrix by any scalar factor and still satisfy the Young-Baxter equation, but we can choose the following value of beta. And then also alpha is fixed because ratio is fixed. So let's choose beta as cosine lambda minus mu wash H minus L. Lambda minus mu wash H minus L plus cosine lambda plus mu sin sin. If you do that, then it turns out that alpha plus beta is equal to 1. And furthermore, we have that R matrix satisfies this so-called unitarity condition. Sorry, no, this is 16th dimension. Okay, now choosing now it turns out that if parameters lambda, u, and u are all real, then the R matrix is R matrix is unitary. It's a really complex unitary matrix, right? And then it can generate a circuit of Q dits with d equal to 4. So it generates integrable circuit, integrable Hubbard circuit, quantum Hubbard circuit. And what is the, well, I mean, we have already shown the transfer matrix, but I can write it again. Now, it's slightly more interesting because it is not of difference form, right? The R matrix was not of difference form, so we have to be slightly more careful how we write transfer matrix. So now transfer matrix reads as follows. Spectral parameter omega, tracing over the auxiliary space, some ordered product of transfer of R matrices. So this is AJ, 2 copies. Now one copy is auxiliary, one four-dimensional copy is auxiliary, the other is physical. It has 2 spectral parameters. One is omega, the other is lambda or mu being flipped. Every other is lambda, every other is mu. So maybe here is minus lambda minus mu. So, okay, so now it turns out, I mean, that you can then, using the Young-Baxter equation plus this relation star, you can show the following 3 kind of identities. First one is that the transfer matrix commutes. Second, it's an involution. Second, that the circuit commutes with the transfer matrix. And third is that the circuit can be written in terms of kind of logarithmic derivative, right? It is now really very different from logarithmic derivative because you can take 2 different spectral values of parameters mu and lambda. I mean, these are now mu, lambda, and u are kind of independent parameters of the model. So they can all be kind of arbitrary real numbers, and this will be unitary circuits. So now it's not clear what you want to call total time, what you want to call interaction, and so on. So it's a kind of rich family of circuits which are all integrable, right? But now what we are after here is, of course, something different. Is when the circuit is a stochastic matrix or quantum stochastic matrix. And that happens, again, as a little miracle, that happens if you take all parameters being imaginary. So, however, if lambda, u, and u are all imaginary, then R is a bistochastic. Well, it's a quantum channel, right? It's a quantum channel. It's a bistochastic. Quantum map. And how do we show that? I mean, the proof of that, there is in quantum information theory, people have a simple way to show that kind of statements, which is the so-called Choi, via the so-called Choi matrix. So the proof goes via construction of this so-called Choi matrix. So of R. So the channel, the R or the map, the matrix of the map represents a quantum channel if its Choi matrix is a state, which means if its Choi matrix is a positive semi-definite matrix with appropriate trace 1. So I mean, now these matrices have 4 indices, right? 4 row indices and 4 column indices because there are 2 replicas and two sides. So if you write them like alpha, beta, gamma, delta, epsilon, psi, eta, theta, so these are like all indices for 0 or 1 or 1 or 2. Then this is like how you identify, and then you just you do the partial transpose with respect to replicas. So alpha, beta, gamma, delta here, and here there is epsilon, xi, and here is eta, theta. And then you just show that this is this, and to show that the map preserves a trace and it's unital, because I claim it's bistochastic, which means it has to be unital and trace preserving. And this amounts to showing that the 2 partial traces, I mean, that this Choi matrix has also some partial traces which are equal to 1. I mean, this is very technical, and I think I should not, I should really spare you with that, but there is a straightforward proof that this goes through. And what is now maybe the last part, which is interesting, is what are the Kraus operators, because I started with the Kraus representation, and that's, for a physicist, is very intuitive, right? To represent quantum dynamics by a collection of Kraus operators, which are really the quantum processes that you should apply on the state. And the Kraus representation straightforward. You remember when we wrote the Shastri SR matrix, there was 2 terms, right? And these 2 terms in the vectorized notation, you can represent already as Kraus operators. So in fact, vectorized notation, right, a Kraus representation would be just this. Well, you can think this is a complex conjugate. And one of those guys is simply a probability. P is now probability to have the k plus. So it's 1 minus square root of 1 minus p is the probability to have square root of probability to have k minus. And then there is this R check free fermions q minus k plus square root of p R check I q plus, and then there is Shastri's decoration. And what is q plus and q minus? Q plus minus is minus I lambda plus minus mu. So these are real parameters, and p is the same as alpha. Alpha was somewhere, which I erased now, but it was explicitly written in terms of Shastri's parameters. Okay, so now this is just like, yeah, if you have these 3 Fermi-Null matrices, right, one has to be decorated, then this process will be integrable and has this simple Kraus representation. Now, I think I have to stop. So of course, this is looks at this point rather convoluted, but I insisted to work on in circuits. There is much more, well, perhaps more intuitive way of understanding this integrability is through the mapping on the level of Lindblad equation. For example, if you look at the corresponding continuous time dynamics generated by the Lindblad equation, then the mapping is between the Hubbard model, Hubbard Hamiltonian, and the XX model with dephasing noise. So if you write XX model with with the Lindblad operators. So if you take XX Hamiltonian, and then you take ramp operators which are square root of gamma sigma z, which is super dephasing. So that's the simplest model. I don't know if you want to call it free or not. I mean, it's a free model with a simple dephasing noise. It's the simplest quantum dissipative system. There's lots of literature dedicated to this model. And it turns out if you vectorize this model, then you have a generator of the dynamics, the Lindbladian dynamics, which is exactly the Hubbard Hamiltonian. So Lindbladian is just the Hubbard Hamiltonian with imaginary u. So times the I, because now this is, or one has to put the I somewhere. So there's a little trick one has to do. I mean, it's still not completely straightforward. There's a little trick one has to implement a canonical one canonical transformation on one of the copies of the doubled Hilbert space in the vectorized notation. But again, I mean, it's maybe physically more intuitive why this connection kind of happens, right? This was realized in the paper almost 10 years ago by Medvedeva, Fabian Essler, and myself in PRL 16. And then Fabian also had a dedicated thesis of his student. So they had a couple of papers with his student, forgot the name precisely, but in 2018-19, constructing some related models based on similar philosophy, which was also integrable. And then there was, I think, two papers which are kind of worth remarking, because they made important progress in constructing integrable Lindbladians and integrable quantum circuits. One was the paper by Chiara Paletta, Marius Delev, and Balázs Pozsgály. It was a PRL in 21. They constructed family of integrable Lindbladians, again, which all are translation invariant, so generalizing on this model. The feature of all these integrable Lindbladians is that the Hamiltonian part was always XX. So that's, again, one thing which is kind of persisting, right? I mean, whatever we try to do, the Hamiltonian part should be free, should not be interacting. So we don't know of any non-trivial model for which the Hamiltonian part, when you switch off the dissipation, would be generally interacting in the bulk, interacting, and would be integrable. So that's kind of puzzling. Yeah? So then there was an interesting paper, 1 year later, by Sue and Martin, Ivar Martin, in PRD 22, where they generalized our construction of Hubbard Kraus circuit using basically the results of these people to generalize them to circuits. So they found additional set of models which were not continuous time, but discrete time models which were integrable in the same spirit. Okay, so now with this, I would like to finish my lectures. So yeah, I mean, as you see, there are plenty of open problems. Yeah, the things when you try to find integrability within quantum dissipative system setup, it seems there are lots of obstacles, lots of constraints. There are some results, but the big picture is kind of still kind of in the air. So thank you.